welcome back and Happy New Year to AP Calculus 2012. Anyway, as we jump back into it, you see we are entering Chapter 6 here. And Chapter 6 we're talking about applications of integration or applications of the definite integral. And if you'll remember from the first semester, we studied what a derivative was. And remember, a derivative was just telling you what instantaneous change was. We were interested in change, and how did we measure it? We measured it with the derivative of a function. So we learned what a derivative was and how to compute derivatives, and then we had a chapter called Applications of Derivatives. So we in the applications were like related rate problems, maximization problems, linearization, and also we analyzed functions with analyzing how functions changed with the derivative. Same thing. Then before the break, we studied the integral. And again, if you're explaining this to somebody who never took a calculus class, you'd say an integral really is adding things up. We're adding up little units or remember we put up little rectangles. We added up little rectangles of velocity times time, so that would have been little distances. Adding up little changes in distances. So an integral was a big adder. Now, once we learned how to integrate, we learned how to take integrals. We learned how to use a technique called substitution. We learned about the fundamental theorem of calculus that kind of brought derivatives and integrals together. You'd see the relationship of one to the other, that they were inverses of each other. But now we're going to go Chapter 6. We take our knowledge of integration and we work on some applications. The first thing we'll talk about, and we'll do that tonight, is the area between the curves, okay? And I'll do a video or two about how to find that. So we want to use an integral to find area between the curves. Then we get into an interesting application called volumes. We'll actually take some of these functions and we'll revolve them around axes to model what a volume would look like. And we can calculate volumes that way. And I've got actually the Khan website. Khan does a lot of very good videos on finding those volumes. So we'll go back and use some of his videos. And then I'll fill in a couple videos with some loose ends. And then we'll talk about the average value of a function. That's what we're doing in Chapter 6. So let's get going then with area between the curves. Okay, here we go. And here I've got two functions up here, right? I've got this top function, the top function on top here, and we'll call this f of x. All right, let me erase this down here, and we'll call the bottom one, if you already got a sneak peek at that one, you see we'll call that function g of x. And what we'd like to know is between A and B, we're trying to find, what is this area here? What is this area that lies between the curve? Maybe this, if you look down on it, maybe this is an outline for a skating rink. Trying to find how much surface area we have on our skating rink. But we want the area between the curves. So what do? Well, how do we find any integral? We started making rectangles. So you see this rectangle here. The rectangle I have A1. And A1, we could get the height of the rectangle. What's the height of the rectangle? Well, it's the function at A. It's the function at A here, f of A, minus g of A. Now notice the function goes beneath the x-axis. It's down here beneath the x-axis. So you might think, well, wait a minute, I got to take f of A plus g of A. Let's just put in some numbers in here to make you see why that would not be the case. Let's say f of A here, that looks to me like, if I'm ballparking that looks like it's 4. Okay? G of A here looks like it's below the axis. I'm going to say, hey, that's minus 2. That's minus 2. This is 1, 2, 3, and my scale's a little messed up. That's minus. So what is this? F of A minus G of E. Well, you could see what's the length of this side? The length of that side here is 4 minus a minus 2. This is 6, right? This length right here that I'm filling in, that would be 6. That would be the height of the rectangle. And if I want to know the area of A of 1, I need the height times the width. Well, what's the width? The width is just going to be B minus A. Here's A. A is kind of hard to see now because it's been covered with red. A is right there. So it's B minus A. That's the interval divided by the number of rectangles I have, which I have n. So if I wanted to approximate this, and you can see it's an approximation because I'm missing some areas here, I could add up those little areas, right? I could add up these little areas right here. And here I'm going to add up n of them. Now, how am I going to get the true answer? We've done this before, right? How do I get the real answer? Well, the real answer, if you want to get more accurate, I want to do more rectangles. How many? Do I go to 100? Do I go to 1,000? Well, let's use our concept of a limit here. And you might say if a limit as n goes to infinity of this, that's going to become what? See, this goes to, now I've got an infinite. Whoa, whoa. I got an infinite number of rectangles, and that's going to become my definite integral, just like we did before. So what happens is I get an integral from A to B, and what happens to the width of my rectangle? The width of my rectangle becomes dx, and I take the function f of x minus g of x, I integrate that. Notice when I do this, this is this again, that's the height. And that is the width. And if I'm really finding areas, this should always be positive. The height should always be positive. We always integrate positive little areas. So it's important you take the largest height, which is positive, minus the littler height. Okay, you take the curve on the top minus the curve on the bottom, such that you get a positive area. So then this has to be the case. F of x minus g of x has to be greater than 0 for all x in order to do this right. Okay, so anyway, that is in general how you find area between the curve. Now let's work a problem perhaps, shall we? And here's a problem from our book. Here's a problem from our book, page 352. The first one is always good to get going with the first one, and we want to find what area are we looking for here? Well, we want this area here, right? We want this area right between the curves. Kind of important to determine now. When you work these problems, sometimes, sometimes there's another area, but you want to make sure you're finding the right region. Okay, so what do I want to do here? I might, it's probably not a bad idea to draw a little rectangle here, right? Just to make sure you understand. When I draw that rectangle, what do I mean? Well, that's my little differential area. And I'm going to integrate the top curve, which is what? The top curve is just going to be 5x minus x squared. X squared, gosh. Minus the bottom curve, which is just x, right? So it's that height minus that height, x. Okay, that is the height of the rectangle. What's the width of that rectangle? Well, the width of that rectangle is just dx. And I'm going to integrate from what to what? Well, I need to know where they intersect, first of all. Yeah, what is this? I need to know the limits. So you might think that, well, at 0 they intersect because of the curve, and you'd be right. But how in general do you do this? In general, you're going to set the one curve equal to the other, right? So I want to set, where does x equal 5x minus x squared? Where is that true? I want to find the points of intersection here. Okay, well, let's solve this thing. 0 is equal to 4x minus x squared. Solving that, I'm going to pull out an x. and I get a 4 minus x. Okay, well, it looks like it's 0 at x equal to 0 and x equal to 4. There we go. So this is going to go from 4 to 0. So what are my limits then? After I did all that work, let's put them in a different color. I'm going to go from 0 to 4. 0 to 4. Okay, you could probably integrate that now. Oh, it looks like I'm already at 10 minutes. What the heck? It's a new year. Let's see if we can start off with the right answer here. This looks like it's going to be 4x minus x squared dx. I'm going to integrate that, remember? So I go, that looks like it's 2x squared. And I'm, powering up and dividing, skipping a step here. But if I took the derivative of this, since it's a new year and I might be making mistakes, the derivative of this, I bring down the 2, 4x. Yeah, that looks right. Minus x cubed over 3. I'm going to go from 4 to 0. And that's going to be what? Well, it looks like it's 2 times 4 squared minus 4 cubed over 3. Which is what? That's 16. That's 32 minus 64 thirds. You could reduce that. I guess we should. Let's not start off lazy in this new year. We'll get that. 32. It would be what? 96 minus 64 over 3. And that looks like to me, I'm thinking I'm at 32 thirds. 32 thirds. Okay, next video, we'll talk about area between the curves, but we'll look from the y-axis. So we got to turn our head sideways, which startles people sometimes. So let's work one of those problems.